Of course, not very hard to define. It's just a collection of numbers from any larger set we want, like the real numbers, or the rational numbers, or the integers. And there are finite sets, like 1, 2, 3, 4, and infinite sets, like the integers. But what's more hard to answer is, what are orderings? Well, an ordering has to have two properties. One, between, it has to be, okay. An ordering only has to have three properties. One, it has to be binary. So it has to be a comparison between exactly two numbers. So if we have m and n in whatever set we want, an ordering in that set has to give us a comparison between those two. Number two, only one of the following can be true at a time. M is less than n, m is equal to n, or m is greater than n. And number three, this property has to be transitive, i.e. if m is less than n and n is less than p, then using those two pieces of information, we can show m is less than p. So those are the three properties any ordering needs to have. But you might ask, well, why not just settle to the regular orderings we have in arithmetic? Well, because there are some other things that we might need to compare. Like, for example, orderings can be useful outside the context of real analysis. Here, I've written the 8 closest stars to Earth. So we've got some that you might know, like Proxima Centauri, Barnard Star, and Sirius, and some that might be a little bit more unknown to people who aren't enthusiastic about astronomy, like WISE 0855 0714 or Lalande 21185. But I'm going to show you 4 different orderings, why they all might make sense. So first is the vanilla ordering that I use just to write them from top to bottom. Well, how close are they to Earth? 4.24, 4.34, 5.96, 6.50, 7.43, 7.86, 8.30, 8.71. By the way, information source from Wikipedia. So that's one ordering we can use. So that's ordering based on distance. But we can come up with a lot of different orderings. For example, we could come up with an ordering by alphabetical. So you could order them by where the stars are in alphabetical order. For example, in this case, Barnard Star would come for first because it starts with a B, followed by Lalande 21185, followed by Lumen 16, followed by Proxima Centauri, followed by Rigil Kentaurus, followed by Sirius, followed by followed by WISE 0855 0714, and then at the end, Wolf 359. So that's a completely different ordering. And then we can come up with ordering by the alphabetical order of their own constellation. And this is the only time we can see an equality relation instead of two things being lesser or greater than one another. Because as you can see, the first two stars are both in the Alpha Centauri system. So we can start with Proxima Centauri and Rigil Kentaurus, which are both in the Centauri, which comes first. So these are both equal to 1. And then we skip to 3 because the next one is going to be Canis Major. Oh, shoot, sorry. So Canis Major actually takes the first spot, with the Centauri being second. And then the third one is a lot farther off, being Leo right here with Wolf359. Oh, sorry, 4. And then the next one is, of course, wait, HIJ. Oh my goodness, sorry, I'm flipping up here. So, fourth is going to be Y08550714. Fifth is going to be Wolf359 because it's in the constellation Leo. Sixth is going to be Barnard Star because it's in the constellation Ophiuchus. Seventh is going to be Ursa Major because Lalande 21185 because it's in Ursa Major, and finally Lumen 16 because it's in Vela. So there, we've got a completely different ordering. And finally, we could even order them by the length of my writing on the blackboard. And I'm just going to go by rough numbers here. So it looks like this one took me the least space to write, followed by Wolf359, followed by Sirius, followed by these three roughly being equal, and then these two being the longest and also being roughly equal. So there are so many different orderings that we can present for these. And it's not like a single one is correct, although some of them may be a little more useful than others. But there are so many orderings that we can introduce to one set. And so that's why orderings are important, and we don't just have to stick to whatever feels right. And this can work within, for example, a collection of other sets as well. We could order them by how many elements they have, or how big the sum of their elements is, or anything else. It doesn't matter. So that's what an ordering is. And finally, let's jump back to the topic of maximum and minimums, because from earlier, you might recall the sets S1, all rational numbers where n squared is less than 2, and S2, the set of all rational numbers greater than 2, whose square is greater than 2. So, what is the maximum or minimum of these? Well, you might remember, they don't exist. So, what can we do instead to fill a spot there? Well, we can create two numbers known as the greatest lower bound, also known as the infimum, and the least upper bound, also known as the supremum. And they are what they say in the name. The greatest lower bound is just if x is less than n for all n that is in the set, that makes x, okay, sorry. Well, the greatest lower bound has to have two properties. One, it has to be less than n for all n in the set. And two, if there's another number that shares this property, if there's some number b that satisfies 1, x is greater than or equal to b. And similar conditions apply with the least upper bound, also known as the supremum. 1, x has to be greater than n for all n in S. And 2, if b satisfies condition 1, x is less than or equal to b. So this is kind of a substitute for infimums and for maximums and minimums. Specifically, this being a substitute for minimums and this being a substitute for maximums. So that's our first lecture of analysis. To summarize, we covered two topics today. We covered why we need the real set, and 2, we covered orderings of sets.